Thank you so much for having me here. And for those of you who are visiting campus, welcome. UCLA is fabulous, and hopefully you're enjoying the excellent warm weather we're experiencing this November. So when I looked at the title of the workshop, I thought to myself, gee, I got to talk about both classical and quantum computation all in about 50 minutes. So I'll try and do that. And the way I'm going to do that is tell you about work we're doing in non-equilibrium quantum systems that is using classical computation. And then for the second half of my talk, I'll tell you about work we're doing in open quantum systems using quantum computation. Okay? And hopefully through this talk, I can convince you that both thinking about non-equilibrium as well as thinking about open systems is exciting, and that there are approaches to both of these problems that can be leveraged by folks here. There'll be various things I'll go over, and part of the intent is that this gets a conversation started, and that we can actually build on some of these ideas during the course of this long program. Okay, so when folks think about non-equilibrium, and I've recently started to appreciate that non-equilibrium is something that folks across fields think about, and it means different things to different people. But the first question I get is, well, why now? We've known that non-equilibrium is important. We've known that thinking about non-equilibrium quantum systems is relevant. So what are we looking at that is important, and what is happening today? And I just want to draw your attention to this slide here, where essentially, with the various techniques on the ultra-fast dynamic side that have become available to us, non-equilibrium has become something that many more people can access. And that goes all the way from thinking about really fast timescales, something that's particularly relevant with the prize this year being awarded for attosecond physics, all the way out to slightly slower times that are still non-equilibrium, particularly in the context of things like spin excitations. And that's something I'm going to talk about, how we simulate some of these and how we think about these really fast timescales for certain processes, even though those look like slow timescales for other processes. Some of the questions that come up when we start simulating such dynamics, well, are you talking about breakdown of the Bohr-Oppenheimer approximation? Are you thinking about things that are really beyond what an equilibrium theory ought to be able to access? And the answer is yes and yes, but. And that's the but is where all the approximations and the dirty laundry kind of comes into the picture. Okay, so with this motivation, I just want to point out that when we think about attosecond, it's an exciting year. And for those of you that do not think about attosecond as a timescale or really fast timescales, femtosecond, attosecond, you're thinking, gee, how fast is that really? And this chart resonated with me, in part because this tells you about something that hopefully we all experience, a heartbeat. Yes, no AI here. So that's about a second, and the age of the universe is about as far away from this timescale as an attosecond is from this timescale, just in opposite directions. So just as you start to conceptualize really how non-equilibrium these systems are, hopefully this is something that helps you keep that in perspective. So when we think about these really fast dynamics, you might say, well, what's the point? What are we doing? Why does this matter for many body systems? Why do we care about non-equilibrium? And part of the answer is that we actually have the ability not only to excite systems and drive them and watch them thermalize, which, by the way, the field of ultrafast has done for decades. For those of you who are students here in the audience, I might take the liberty of saying before you were born. But that is a different set of excitations than what we're thinking about today, with the very precise selective control that is accessible with experimental techniques. What we can do is drive a system and then think about creating a new set of states using that drive, right? And that should strike you as being slightly counterintuitive, because essentially I'm pumping an energy into the system, which typically means I get to some excited state and then I start watching some thermalization happen. We're talking about something fundamentally different here, and that's important because in this scenario, we can think about various kinds of collective excitations, phonons, magnons. Pick your favorite collective excitation. Pick a particular energy range where you can access it, selectively drive it. And something I'll convince you of in a few slides is that actually driving via the phonon can be particularly important. So use that to access the carrier dynamics. There's a fair bit of element specificity. This is something that is new from the experimental side, something that was not accessible to us previously. And there's also very precise control over symmetry and symmetry breaking. So in some of these quantum systems, what we'll observe is that you're able to, say via the phonon, drive a phase transition, and you're able to stabilize something that ordinarily in equilibrium would not exist. Okay, so I don't want to belabor this point too much, but just reemphasize that this is across a very wide set of spectral bands. So going all the way from the X-ray to microwave. And in parts of my talk, I will live somewhere in the IR. Some parts of my talk, I would venture out into the terahertz. But a lot of what I'll talk about is also relevant to work happening at XFL Techniques, work happening, say, at the LCLS. And I think that now is particularly a good time to think about it, especially as more experiments come online at LCLS for how we can predict such non-equilibrium states. So this is usually the point where somebody typically quite distinguished in the audience says, well, what's different here? This seems like what we've been doing in the field for quite some time. How is this fundamentally different, right? And again, from a theory standpoint, you can think of this now in terms of a potential energy surface relative to your favorite either lattice or electronic coordinate. If I'm probing the system, I'm sitting somewhere in the bottom of this trough. Okay, that's fine. That's something I would start with an equilibrium theory, slightly perturb things, and I hope to end up roughly in the right area with my answer. But that's not what we're thinking about. We're talking about things where perhaps you're using the drive to switch between two degenerate ground states, excite a metastable state, thinking about critical phenomena, and very, very importantly, thinking about strongly nonlinear phenomena, particularly in the context of nonlinear phononics, right? And I'm going to introduce this idea that nonlinear phononics is something that is selective enough that we can actually apply non-equilibrium calculations, that we can actually think about this in a way that's controlled enough, but also exciting that we're far enough away from equilibrium theories that some of these new methods need to be developed. Very provocative result, and I'll leave this here for those of you who are about to zone out and say, this is another condensed matter talk with lots of acronyms. I'll just say that there are claims that we can, by picking just the right phonon, drive, say, the parent cuprate here, YBCO, and not only use it to drive the system, but to actually stabilize this very well-known superconductor above TC. So there are really, really exciting claims out there that non-equilibrium can do things that you would really not be able to do with equilibrium or low energy excitation of these systems. There's a reason to develop some of these new methods. So this is around where you might start to ask, what do you mean by new methods? Is there a new acronym that you're about to introduce? I'm not. In fact, turns out a lot of what we do in the group is combine methods both from quantum chemistry and condensed matter theory to access some of these non-equilibrium phenomena. And I won't say that we have a method that is now ready to replace every method that you've seen out there, but I do want to point out that there are some methods where we've done significantly better than existing techniques. And one context for that is with light matter interactions, particularly thinking about a slightly different regime than the one I just introduced, where we have correlated light matter interactions, where we treat the QED and the electronic structure theory at the same level of quantization. I've given other talks on this, including one at IPAM, so I will just put up one slide on this and refer you to, I think those talks are also recorded and still available from IPAM. But just want to introduce that there is a set of techniques that we and others have been working on that go beyond non-equilibrium Green's functions approaches, ones where you formally and computationally treat QED and electronic structure theory at the same level of quantization. Now you might ask, what electronic structure theory? This could be QED plus Hartree-Fock. This could be QED plus mean field, QED plus time-dependent density functional theory, QED plus coupled cluster, or all the way up to FCI. In fact, we have recent results showing both QED, FCI, and QED, CCSD singles doubles. So just beyond singles doubles, I'm sorry. So go ahead and take a look at those if you're interested, and then I can tell you more about why some of these methods are actually exciting for observables in this correlated light matter regime. Okay, But back to what we're really talking about in this context, which is staying far away from equilibrium. You might be able to argue that QED plus electronic structure theory is still equilibrium, and you might just be right. But where things are quite different is where perhaps we're using the phonon, which I alluded to already, driving it to create new non-equilibrium states. And a friend calls this just the right shaky, right? So you might think, well, what's happening there? The idea is I pick just the right phonon, I drive it, I use that then to control the other order parameters in the material, right? And this could be using the phonon to control the magnons, using the phonons to control directly the superconducting condensate. There are various ways of going about this. It could also be driving the phonon then to find something that is optically silent and kind of going through that vibrational pathway. So this is a field that has really taken off, in part because we can think of these as being a really nice way of controlling the magnetic order parameter in particular. So there are results where folks have shown, we and others, that you could start out with an antiferromagnetic ground state, and from there, either using linearly polarized or circularly or rotated light here, you could actually create either a ferromagnetic or a ferromagnetic reverse state, depending on how you drive it. So this could essentially be a way of using light to control the magnetic order without directly coupling to it. And this right shaky is quite general. Actually, yes, go ahead.
Sorry, I had a dumb question. So in these calculations, how are you setting? Like, are you kind of discretized? You've got some kind of model for the electrons and some kind of ab initio Hamiltonian, and then you have them coupled to some kind of discretized, like phonon type model,
okay.
And then you're doing the time dependent.
So I haven't gotten to that point yet, but since you've asked, let me just answer that. In this particular context, what was done was treat the magnetic material with the electronic structure theory that's necessary. You wouldn't be able to do this with mean fields. Kind of need to have dynamical things incorporated. That is without the drive. Then you set up a model Hamiltonian where you parameterize using the electronic structure theory. You get the phonons from a separate calculation. You include that in a way that you can then also have the drive, because wonderful things like I'm using linearly or light that's rotated 90 degrees, that's not something that's easy to incorporate into the electronic structure theory, but it's sufficient for us to take some of those parameters from ab initio calculations and then parameterize a model Hamiltonian.
So it's like an ab initio then to like a Hubbard-Holstein type, or is there a different?
Slightly different. I'm going to get to that here in a second. And devil is in the details in the sense that some of these systems, there are specific systems I'll introduce where we're treating the non-equilibrium part of the problem, and also questions like what are the phonons doing? How do we actually think about both the excitation and the ring down associated with the phonons becomes a little bit complicated. But I haven't gotten that far yet. Yeah.
Is there any issue about this being stable? I mean, for ground states, we learned that there's some decay to equilibrium and there's some stability. How does it come upon in you must have some stability to do anything, right? At least a small time interval?
That's right. So yes. So in the context of magnetic systems in particular, and this is actually quite important, talking about a state like this means that we need to be at least on the order of a few hundred femtoseconds. It's not useful for us to talk about such ordering on the order of, say, attoseconds. That's too fast. And so this is that point I was making initially about non-equilibrium for different types of excitations means different things. And in this case, we are very firmly in the picosecond regime, and we're stabilizing some of these states all the way out to a few nanoseconds on a good day. Yeah.
And are there enough theoretical results which say it is stable for that time, or is this more experience?
Well, I'm going to try and convince you that our calculations show this is stable and that it's reasonable to think of this transient state still being able to live for that long of a time. Yeah. Okay, so hold both of those thoughts because I'm getting there. All right, so maybe I've belabored this point already, but just for people who are seeing this for the first time, this idea of driving via the phonon, this is something that lives in the picoseconds, whether it's phonon-driven superconductivity, ferroelectricity, topological symmetry breaking, or even magnetically addressed vibrational excitation. So just in terms of timescales that we're interested in. Now, for those of you who come from an optics background, you might immediately look at this and say, I have light. It's interacting with something magnetic, right? That sounds like optomagnetic effects. Why go via the phonon? Seems very, very complicated. Why are we doing all of this, right? So to answer that question, let me just point out that yes, there are effects that we would normally invoke. So the Faraday effect, the Cotton-Mitten effect, and more importantly, the inverse Faraday effect and the inverse Cotton-Mitten effect. These have been around for quite literally decades, right? What we're now talking about is instead of thinking of directly accessing the magnetic order parameter with light, thinking about going via the phonon. And you could think of these as phonomagnetic analogs of these optomagnetic effects. And this analogy goes pretty far. In fact, we can talk about a phonomagnetic effect that is essentially the phonon inverse Faraday effect or the phonon inverse Cotton-Mitten effect, and they look exactly the same. In fact, we were so excited by this that we said, why don't we go about classifying some of these effects, write out the magneto-optic and the optomagnetic effect, and then figure out if the phonon inverse and the phonon inverse Faraday and the phonon inverse Cotton-Mitten would look similar. So it turns out that the important thing here is that you coherently drive the phonon. Okay? So just driving any phonon, no good. Driving the phonon with incoherent excitation, no good. But if I coherently drive just the right phonon to first order in magnetization, I can have a phonon analog to the inverse Faraday effect. And to second order, this would be the phonon inverse Cotton-Mitten effect. And what we would create now are fields. These are fields inside the materials, not the kinds of magnetic fields that you'd be interested in with your fridge magnet, putting up pictures there. We're thinking about something that is an effective field that lives inside the material. We call these well, as you might think, effective magnetic fields. And the effective magnetic fields associated with these two effects can be actually quite large. What I'm going to show you in the next two slides is that these can be substantially larger than the optomagnetic effects that have been thought about for quite some time.
Can you also drive the longitudinal phonon coherently?
Yes, so in this case. So what you would want is if you were looking at something that is optically silent, you would pick optically active mode, and then perhaps use a cavity to then essentially impedance match and drive the phonon you're interested in. And that's something that we and others have shown in other work. I wasn't planning on talking about that here today, but I can show you results where we've done exactly that. You could also have a scenario, which we've also looked at, where, say, I parametrically drive the Higgs-like phonon mode in these materials, and then from there end up with a pair of Goldstone modes, which are possibly optically silent. So that's something that we've looked at as well. And all of the order parameter dynamics associated with the structural order parameter, which is where this work was done, has analogs in AMO as well. Yeah. So, okay, so I keep calling this an analogy, and let me just mathematically show you what that looks like. To think about the inverse Faraday effect, I want to calculate the susceptibility. That's something I can do. This is something that many ab initio methods would be able to do quite regularly. Now, when you want to think about the phonon inverse Faraday effect, and by the way, this susceptibility would be essential then for us to calculate the effective optomagnetic field. What we want to do for the phonon inverse version of this is get the dynamical matrix, and then use that dynamical matrix now to think about the phonomagnetic component. And this is where thinking about the phonons at the right level of theory, as well as treating the electronic component at the right level of theory, becomes important, which is not something that people conventionally think about in these optomagnetic effects. But assuming we can do that, assuming we can incorporate some of these results in these Q.Q type terms, we should be able to calculate this phonomagnetic field. And that's exactly what we do. In fact, we not only calculate this phonomagnetic fields for systems that are well known, like nickel oxide, but also started to look at other systems where such effects can be quite large. I want to give you an example of that in a rare earth trihalide, cerium trichloride in particular. This is an exciting system because a lot of things are happening here. I have a phonon I'm going to drive, but I'm also going to claim that somehow there is a component of chirality here. This is an achiral system. If you look at it, it's quite symmetric. I and others can see that, literally looking at the unit cell. But what you realize is that this actually has a pair of modes. They're both E1U modes. and they're essentially of opposite-handedness in some way. And what we can do in this context is just pick the right mode in order to get a very large effective magnetic field. So for this system, we looked at the eigendisplacement. So cerium maps out the circular orbit. You get these nice elliptical orbits from chlorine. And this is what the ground state looks like. So these are all calculations done at an ab initio level. Now, the hard part is how do you say that I have enough spin-phonon coupling that is selective associated with a particular mode in order to actually get these fields, right? So I'm driving the phonon through some spin-phonon coupling is how I'm going to end up with this giant effective magnetic field, and that's exactly what we established for the system. So I want to draw your attention first to this plot on the left where we're looking at the amplitude trace relative to time. This is not always the easiest to look at, but what I want to point out here is that we come in with a very short terahertz pulse, shown here in green. Immediately, and that immediately is important because that means there's no lag between driving the phonon and seeing a response. That's relevant. We start to see both the E1U mode that corresponds to 5.9 terahertz as well as the 4.8 terahertz mode coupling to this incoming field. That oscillation looks different for the two modes, and that's because one of the chiralities, the 4.8 terahertz mode, actually couples a lot more and gives you a lot more of this spin-phonon coupling than the other one. And that shows up a little bit better in looking at the effective magnetic fields, and your eyes are not deceiving you. This is field in Tesla, not in millitesla. But remember, this is an effective magnetic field. We can get actually very, very, very high fields that persist for few picoseconds using this mechanism, okay? So this is a long enough transit field. This is something that ought to be relevant even for applications that use such synthetic magnetic fields. We've done calculations associated with the fluence dependence. We're not melting anything. We're not destroying the order. This is something that ought to be experimentally relatively easy to realize. So you might ask, well, what about other systems? You're claiming that you can get really, really high fields here. You've used the word giant in the title of your paper. Yes, 107 Tesla, I would say, is a giant effective magnetic field. And that is in contrast with other systems like nickel oxide, where we also calculated and eventually was measured the phonon inverse Faraday effect. That's on the order of a few millitesla. And some of the other systems have been more on the order of a fractional Tesla as opposed to tens of Tesla. So this is an experiment that is now underway, and folks are actively working to realize this in cerium trichloride. And I want to say this is something that is general beyond cerium trichloride. There are other rare earth trihalides. What we think the ingredients are is large spin-phonon coupling associated with the 4F paramagnetic spin that shows up in cerium trichloride. Is that a complete set of design parameters? Probably not. There are probably other things that we need to incorporate. But in this case, finding the right chiral phonon, thinking about this spin-phonon coupling, being able to do those two calculations ab initio, and then being able to get this drive in there explicitly was sufficient. So when we put this out there, there's a lot of, yes?
Sorry, so on the, before you were talking about how you need to kind of find the appropriate electronic structure theory to describe that system, and then kind of the way you describe the phonons has to be. So what do you find for these types of systems for the electronic structure treatment, like the ab initio treatment?
Yes.
What works, and how do you?
So cerium trichloride, we cheated a little. We did a little bit of dynamical mean field theory. That was sufficient to figure out just the right lattice, right? Because it turns out that if you have, say, something like density function theory, it would the lattice would end up wrong, even though we're not looking at direct optical excitation, which is typically where that failure mode shows up. In this case, the fact that there are some correlations associated with this magnetic order is something that you wouldn't be able to capture. Dynamical mean field theory, just fine for cerium trichloride. It's also fine for nickel oxide. Could you get more complicated? Absolutely. In fact, somewhere in the review process, somebody asked me why I'm not doing DMRG on this, and I said, well, have you looked at the unit cell? So there are things we can do, and then there are things that are exceptionally hard for us to do. The important thing is to treat the phonons beyond a frozen phonon approximation, right? So when I think about displacing the phonons, frozen phonon, for those of you who might not have this as working knowledge. I can either displace them all into the same eigenmode and think about that response, or I can actually look at the dynamical component there. And I'd say the dynamical component is what is important. What we don't do here for this system that we're working on in other contexts is some of those 3, 4, and higher order phonon modes. Those would be relevant. Those would particularly be relevant, I'd argue, for the thermalization behavior. So if you wanted to actually figure out why this lives for 6 picoseconds as opposed to 60 picoseconds, I'd actually want to look at that explicitly. We haven't done that for serum trichloride, but there are other systems where we actually have done that. Any other questions on serum trichloride? Yes?
Is electron-phonon coupling calculated by EPW, or are you using some other?
We have our own method to do that, but it does something very similar to EPW.
I see. And quasi-particle energies are coming from DMFT? Or
That's correct.
Okay.
Yeah. It's you could do, well, you'd start out with DFT, do a DMFT correction to it, or in some of the cases, like this KTO system, those are not our calculations. So nickel oxide serum trichloride are ours. I believe they just used simple density functional theory for the lattice. And that probably is underestimating some of the order, but they argued that what they were really looking for was something else. But that's not our work, so I shouldn't comment any further on that. Yeah. OK, so the choices are many. In fact, I'd say this is a scenario where the parameter space is so large, I could go via an infrared resonant Raman effect, find the right R active phonons to somebody's point earlier. How do I know which phonons, what is actually coupling? I can go via that, go to a Raman active phonon. I could go directly via the magnons. The parameter space really is giant here. And as we started doing this, we added an additional complication. Why stop at one magnon? Why stop at one phonon, right? You would say, if you're calling it a nonlinear process, if you're saying this is actually out of equilibrium, fine. Multiple excitations ought to be sufficient. And that is something that we've shown. We've actually shown that you could do difference frequencies, some frequency type processes. You could do up conversion. You could think about parametric down conversion. There's like a very, very large parameter space associated with this. In fact, we're calling this idea nonlinear magnonics, and I encourage all of you to think about that, particularly if you're able to access this experimentally. So as we were putting this paper out there, a lot of folks said, great, so you can write out this matrix, you can calculate this effect, but just because you say the effect can be calculated does not mean it will exist above all else, right? Because once I start exciting the system, other things can happen. And I haven't shown you anything that has truly established this as being non-equilibrium. I've only said that this is non-equilibrium. So let me show you a little bit of evidence for why this is fundamentally non-equilibrium. And now my story is going to pick a specific system where hopefully we don't disagree on anything, because this is a pretty well-defined and well-agreed upon system called YTO. This is something where you have a very well-defined EG T2G split. It sits on the border of ferro and antiferromagnetic order, right? So what we are, and it undergoes a distortion that is so well characterized that it's a type of distortion, a gadolinium ferrite type distortion. You could cause this distortion to happen via strain, doping, all of that good stuff. What we're going to show is that the drive is what allows us to control whether you sit on the ferro or the antiferromagnetic side. And the claim is going to be that if I were looking at just the equilibrium order, I could actually change the TC by driving, but I can sometimes selectively stabilize the ferromagnetic order, and some other scenarios I can selectively stabilize the antiferromagnetic order, okay? So to show you that, how am I going to measure it? How am I going to actually establish this? This measurement is going to be a time-resolved magneto-optic Kerr effect, MOC. And the concept here is I pick specific phonons. They're resonantly driven. Remember, we have to coherently drive these. We have to actually select these modes. Now you might ask, how did I select the modes? So we pick the modes with the largest magnetic field dependence. So if you look at the spectrum here, there's a 4 terahertz, a 9 terahertz, and a 16 terahertz mode. And these, we are now going to look at B2U mode. So we're going to think about this on the B axis. So the axis is going to be relevant here, okay? So with all of that, pick the modes, and then probe the magnetization. Essentially, this is going to be a rotation that shows up. And I can do this as a function of field, temperature, fluence, all of that good stuff. OK, this is the plot that you really need to pay attention to. So now, MOC, the angle, is what we're looking at, right? And remember, we sit at the border of ferro and ferromagnetic order. So you might see that in two of the cases, the 9 terahertz and the 16 terahertz mode, I have a positive Moog angle here. And for the 4 terahertz mode, this goes in the opposite direction. Your eyes are not deceiving you. This is actually towards that claim that in some cases, we're able to stabilize the ferromagnetic order. And by driving a different set of phonons, we can stabilize the antiferromagnetic order. Because remember, if by picking all the phonons, all we were doing was stabilizing one of the types of orders, that would not be selective control. That would just be some luck. In this case, we actually have very selective control. And in this system, YTO, prior to our work, this is very well established. The TC is about 27 Kelvin. That's what I'm calling the equilibrium TC. What you're seeing here for the 9 terahertz, the pump mode with the most prominent response here, is that we're able to stabilize this, depending on how you want to cut this off, all the way up to about 80 Kelvin. So that's a big change in TC. This is stabilizing the ferromagnetic order well above what you would expect, and this is directly now the optical stabilization of this order going via this phonon mode. So now if you've been looking at this trace carefully, and if you've seen this in the past, you might say, so it looks like the rise time is quite fast, but the decay is very slow, right? This is now hundreds of picoseconds. Previously, we were looking at times that are on the order of single picoseconds. So in this case, it looks like this order persists for a very long time. Why is that? Traditionally, when something persists for a long time, there's some kind of bottleneck, but that doesn't explain the rise time being fast. That only explains why the decay is slow. So what we start to think about is perhaps if we think about this system as being driven beyond where the drive is turned off, we might be able to describe the phonon ring down. And yes, turns out that even after the drive it goes away and you're just probing the system stays in this effective driven state. You can essentially think of it as there's some memory within the system that looks like this kind of built-in floquet. Okay, but that still only gets us a part of the story. We reconcile the rise time being really fast because it's a sideband. So towards a question that came up earlier, why do I need to treat the phonons the way we do? Why do we need to think about this beyond just the frozen phonon or even think about multiple phonon type excitations? That's because we need to have the sidebands, we need to understand the phonon ring down, and we need to understand if there's an angular momentum bottleneck. So there's orbitals here, there's spin-orbit coupling. This is kind of the trifecta system. And of course, there's interesting contribution from the phonons. So hopefully at this point, I've convinced you that we do have something that is truly non-equilibrium. And this is a system that was our fruit fly system. There's a series of papers on this that have appeared. I think I had the references somewhere. But that still is in this phonon inverse Faraday effect scenario where I have a phonon and I have a magnon. And that's the coupling that I'm looking at. I promised you truly nonlinear magnonics, and I want to draw your attention to another system that we've looked at, erbium ferrite. This is a system where you can think about the two sites, so the ordered antiferromagnetic and the ordered ferromagnetic sites. You can think of the magnons associated with that. Think about coupling between those two and use that for magnon field upconversion. This work should appear in Nature Physics any day now. So point being that these non-equilibrium effects are not just ones that we are dreaming up. We're not just writing out matrix elements or processes that are going to be vanishingly small. These are actually effects that matter, and hopefully some of you will start to calculate these using your own methods. So before I switch to the second half of my talk, I still have plenty of time, right? Yes, okay. I just want to acknowledge that the work on the non-equilibrium dynamics, I won't really talk too much about the topological quantum matter work, but this was primarily done by John Curtis, who was a postdoc in the group, and by Dominik Juraszek. Dominik is now a junior faculty member at Tel Aviv University. So now, for the second half of my talk, for those of you who came to learn about the quantum computation component, let's switch our attention to open quantum systems. Everything I talked about so far was on a classical computer. The hope is that by the end of this, maybe some number of years down, all of those non-equilibrium processes can fit on a large quantum computer, but I haven't gotten there yet. Maybe others have. But things I can do on a quantum computer today involve open quantum systems. And let me just tell you a little bit about open quantum systems and why we're interested in these. So there are master equations for treating Markovian dynamics. It's been around for a while. Redfield and Lindblad. By the way, some of you might know Lindblad as the Guarini, Kuskowski, Sudarshan, Lindblad equation. Most people just call it Lindblad. And the idea is that this is typically derived under the Born-Markov approximation. So you end up with three terms. You have the closed evolution, you have the summation with the Lindbladians, and then the anti-commutator, right? So we're familiar with this, and this is, by the way, something that lots of other people have worked on in the last few years. What we've become interested in are systems where you go beyond the Markov approximation, where you're looking at some degree of non-Markovian response. And to somebody who doesn't mathematically think about non-Markovian systems, but very much from a physics standpoint, I'll just heuristically describe it as some backflow of energy or information from the environment back into the system. Okay? There are more rigorous ways of defining what is non-Markovian or how non-Markovian something is. I'm going to stay away from that and just tell you that it's an active field of study. What becomes more relevant for us is that we now need to think about generalized master equations, for example, the Nakajima-Zwanzig equation, to capture such non-Markovian dynamics. I almost said non-equilibrium, but no, non-Markovian, no. And in this context, you might say, well, that doesn't seem so hard. Why don't I just go ahead and directly implement this? This should be just fine. Well, it turns out that when you start doing some of these calculations, it is easy to lose the complete positivity of the density matrix, which makes this result then unphysical at that point, right? So what we and others have done, primarily work by Professor Karehe Marsden, formerly a postdoc in the group, have been to introduce this approach called an ensemble of Lindbladian trajectories, which is, as it sounds, instead of directly propagating this, I can take a bunch of trajectories through the system and then eventually have an ensemble of these. And it's a little bit of an art to figure out how large or big of an ensemble we need. It turns out that most of these are actually quite reasonable. And then I can take an ensemble average over a bunch of these Lindbladian trajectories to retain the complete positivity of the density matrix. So this is something that work previously by Karehe has shown, both on classical devices and more recently on quantum devices. So our first foray with this on a quantum device was to say, can we actually look at a simple model, something that we can also do exactly like the Jaynes-Cummings model? And can I do that in the strong coupling regime, both on-off resonance, and take this master equation and map it onto an actual quantum device, okay? So everything I'll show you so far, or not so far, but in the next minutes. Is that a hand? Yes, go ahead.
What is intuition in your method? Because basically, okay, you have your non-Markovian process, which is a time integral, and you're going to approximate with an ensemble of Lindbladians, which is that you have Markovian processes, and
yep.
it right away, right? So the idea, I would say, is that the average is going to give you your time integral, but I don't see it clearly. Can you give me some intuition into why that will work?
Okay, so the way I would think about it is that because I have a sufficient number of these Lindbladian trajectories, I capture the dynamics without ever losing, but since it's within Markov, I never lose the positivity of the density matrix. And eventually, there's a trial and error component to this where I take a large enough number of these trajectories. So if I take only a handful, I see that I still have all the issues associated with directly implementing Nakajima-Zwanzig. With a large number of trajectories, that goes away. I don't have any more intuition beyond that in terms of the structure of the problem. Perhaps somebody more clever than I would be able to pick out some mathematical structure associated with that. We haven't seen any, you didn't ask this question, but I'll just say this. We haven't seen that much in terms of the initial state dependence or picking just the right, that stuff doesn't appear to matter as much as you would expect in certain other methods. Yeah.
But according to your equations, you do an approximation of this interval, and the interval is an average over the Lindbladian, so it's kind of an approximation of that interval. That
Absolutely.
And
yeah.
You do a certain number of terms which are relevant. I mean,
so you're right, it's an approximation, but I'd say that the approximation ends up being remarkably robust just by taking a large number of these trajectories. Yeah. it ends up being more robust than trying to brute force a problem and then without really understanding why, sometimes losing the positivity of the density matrix, right? So I think that's the trade-off here. Yes, yes, and yes.
You can go ahead.
I was just curious, does it converge to to some kind of maybe TCL4, or I forget what you were comparing to, but does it converge in the limit of an infinite on?
It does.
On some,
Yes, yeah. Was that your question as well?
No. So if I were to simulate this master equation exactly by computing the exact number kernels, all exact methods scale exponentially with the time. So it seems like you're sort of hiding that exponential cost under the rug of
The ensemble.
number of trajectories.
Yep.
Will they blow up eventually, or if you're in a very non-Markovian regime where memory kernel doesn't decay so quickly, so what do you do?
You are right. There are scenarios I could construct. I could think of something very, very strongly correlated like a spin liquid. And if I start to say, well, that's my entire system, and I directly implement this, it will blow up.
But it blows up producing physical trajectory, or just doesn't make sense? Is it better to do TCL4 at that point, or
Yeah.
what's the expected behavior for the failure?
I think I'll give you an answer now, and then we can discuss this in some detail. I'd say at some point the method just doesn't make sense for the systems that we're looking at. So something that is like Jaynes-Kovics, but in a strongly coupled regime, no problem. Something that has very, very long-range entanglement, I think there are other ways of going about this problem. Yeah. OK, so let me just show you what was done initially. So you might intuitively say, well, why are we mapping this problem onto a quantum computation framework? Well, because A, we can, and we wanted to show that we can. And we wanted to show that there's some advantage to being able to do that. So let me draw your attention to the plot here. We're comparing, remember I said we could do this model exactly. There's a reason for that, because we are comparing the exact and a few other methods, including TCL4 that was just brought up, and our ELT method in red. Note that the ELT is not a fit to the exact. It just directly follows the exact dynamics associated with the system. So it's a remarkably robust method for at least such a system. And I'd argue that this method works really well for things that are in the regime of quantum optics, perhaps not in the regime of other condensed matter systems. So what we do here is go through a set of dilation decomposition methods, plus this ensemble method to actually capture the non-Markovian behavior. So perhaps the question that's been coming up a little bit, and just to kind of prime things a little bit here, is do we need things to be in this ensemble method in order to be calculated? And I argue no. In fact, there are other approaches to thinking about simulating open quantum systems using quantum devices, right? And the first one I want to show you is this unitary decomposition of operators. This is a general algorithm, even though the results I'm going to show you are for a very specific case. OK, so we have this algorithm. This is work with David Mazziotti's group at the University of Chicago, where we show that any operator essentially can be decomposed as a linear combination of, at most, 4 unitary operators. So I can start out with something that is quite general. It need not be itself unitary, but the fact that I have this linear combination of 4 unitary operators allows me to then do this problem on a quantum device. We show this so far for a 2-level system, and we show it in the 0 finite temperature kind of regimes. I'm going to run out of time here, but I just want to emphasize, let me just talk about this a little bit longer. So now we use this kind of decomposition. And this decomposition holds in the limit that this parameter epsilon is small. That's something we spend a fair bit of time on. So we actually evaluate this by Richardson's extrapolation. For those of you who are not familiar with that, we can talk about that in some detail. this actually provides a generally quite robust way for us to start out with a general operator, pick at most 4 of these unitary operators within this small epsilon approximation to be able to do this decomposition. So there are 2 plots I'm going to show you here. So anything that has these jagged kind of dots, these are on actual devices. This is the Athens device. The circles are the CHASM simulator. And then, of course, since we picked a system where we have an exact answer so that we can actually benchmark this, are shown in solid lines. So this is now, of course, the lines are the exact Krauss evolution, which you can do in this context. And this is now about, I want to say 2 to the 13, but I'm looking at my notes and I don't have that here, for a 2-level system in kind of a general amplitude damping channel. And we have 2 states, two scenarios here. This is the 0 temperature, and this is the finite temperature case, just looking at kind of the population dynamics here. So this is essentially a simple, but hopefully easy to follow implementation of this idea that we can actually do a unitary decomposition of general operators and map that onto your favorite quantum device, and it ought to work for a few different systems. So while this way of doing this decomposition is important, there's another kind of approach, right? You could also think about unraveling the master equation. And there's a whole class of these things that people have done in the past, particularly thinking about the unraveled Lindblad equation. So this is essentially, you write it in a vectorized form, you break it down, and that ought to be something that realizes essentially the same scenario as this, but perhaps less susceptible to this criticism that this epsilon parameter being small is an approximation. So we went ahead and did this, and this is also work together with Asiati's group, where we looked at generalized amplitude damping channels. This is just on simulators. There are some technical reasons for that. I don't want to go into it. But this is a scenario where we look both at a 2-level system, and since we got sick of looking at just a 2-level system, also at a transverse field Ising model. So again, still simplified, but maybe less simplified than before. And this is a scenario where we have on-site and a set of terms that describe the nearest neighbor type coupling. Okay, so in all of these scenarios, I want to draw your attention to the fact that we can implement this method, even though we haven't shown this itself on a real quantum device. Being able to do it on a CHASM simulator, being able to kind of map it is an advance. And the dynamics that we see here match the exact dynamics really, really well for a variety of different field strengths. So small h here is the field, so we can actually crank the field up and still see fairly good results. So taking that a step further, and I'm really trying to cram in all of this open system stuff into the last few minutes, but hopefully just get a conversation going. I'm here all week, so you can ask me about these essentially all week. So originally, I said we have a combination of decomposition and dilation. This is now primarily a dilation-based approach to simulate things that are non-unitary, but using probabilistic quantum computation. And I want to draw your attention to the fact that we're only using a single ancilla here instead of other ways that people have gone about this. So we and others, and I don't want to go too fast over this, but we have all kind of thought about this SVD type approaches to take any general operator, decompose it down, be able to do this on a quantum device. So there's a whole class of methods actually around this that are developing. And I encourage you to talk to not just me, but also some of our group members who are working on these methods. In fact, I'd argue that this is a slightly more efficient route than the unraveled master equation that I was just talking about. So some of these calculations we've also done now more recently on the Lagos device. I feel like at some point IBM is going to run out of cities to name their devices after, but not yet. And for those of you who've been tracking this, there are much larger devices that are available, but just kind of want to point out that this is a scenario where we've done this calculation. Okay, in the last maybe 2 minutes, I'll just say that this need not be for simple 2-level systems or for Ising models that people can do in a classroom intro condensed matter setting. You can also do more complicated problems, including ones that are established, like the FMO complex. So many others have done the FMO complex, and I don't want to claim that we're doing something here for FMO that wasn't known, but just to demonstrate that we have the ability to treat the full open system dynamics of a complicated system like FMO, 3-site model, but you can do many more sites than that, and to be able to track the open system behavior here. And it turns out that this tracks behavior that's been predicted by other methods quite well. We can actually look at it again over long times. So for those of you who are interested in our work on FMO, Scott Smart as well as Scott Nee have thought about it. We've also worked with the group of Sabri Kais and continue to work with the group of David Mazziotti and my former postdoc Knee on this. I won't have a time to tell you about some of these other things, but just since I see there's somebody who thinks about excited states a fair bit here in the audience, just for you, I'll include this. We have, and this is maybe my attempt at combining what we've introduced for non-equilibrium using classical computation and some of the ideas in quantum computation. We think we have a way of extending these quantum solvers to treat excited states, particularly this idea of a contracted eigensolver that was introduced by Scott Smart and Davis Wallach. We think that, in fact, this gives us a pretty good basis for treating excited states, not just slightly excited states, but eventually even highly excited states. Of course, so far, all we've looked at is dissociation of square H4, so not something that is too exciting, certainly not one of the large systems that we were interested in from a non-equilibrium standpoint, but we've contrasted it with FCI and some of the other methods. So I encourage you to ask us questions about it. And if you don't wish to ask us questions, at the very least, please take a look at our archive paper on it. So with that, I want to acknowledge the people who've done the work on open systems. I've called out Scott Smart, who's in the audience. Scott, you can wave. Scott Nee, Joe Peets. Joe, you can wave as well. And I encourage you to ask all of us questions in the next day, several days. So with that, thank you for your attention. Happy to take any more questions.